Good morning everyone. I am Garima from BSc Chemistry Honors first year. Today we are going to start our chapter 1 of organic chemistry, that is structure and bonding. Introduction to organic chemistry. The term organic compound was originally applied to compounds such as sugar, alcohol, oils and fats which are derived from vegetable or animal sources, that is from living organisms. This was done in order to differentiate such compounds from inorganic substances such as common salt, sulfur and metals which are obtained from mineral resources. The study of organic compounds gradually began to develop as a separate branch of chemistry, which came to be known as organic chemistry. The chemistry of inorganic compounds was therefore distinguished by calling them inorganic chemistry. Vital force theory. In the earlier days of the growth of organic chemistry, it was considered impossible to prepare organic compounds in the laboratory. Berzelius 1815 suggested that organic compounds could be produced only under the influence of some mysterious forces existing in living organisms. This force was called vital force, from the latest word vita, which means life, and the theory of Berzelius came to be known as vital force theory. However, in 1828, Wohler synthesized urea, an organic compound present in the urine of animal, from ammonium cyanate, an inorganic compound obtained from ammonium sulfate and potassium cyanate. CH4 NH4 twice SO4 plus 2 KCNO will give 2NH4CNO plus K2SO4. NH4CNO will give NH twice CONH twice, which is urea. This synthesis of an organic compound in the laboratory shocked the faith in the vital force theory. In 1845, Kolbe synthesized acetic acid from inorganic sources, and the laboratory synthesis of many other organic compounds soon followed. Consequently, the idea of vital forces was completely discarded by 1850, and it was firmly established that formation of organic compounds does not depend upon any special forces. Thereafter, the number of synthetic organic compounds began to rise at an even growing rate. Modern definition of organic chemistry. With the rejection of vital force theory, the major difference between organic and inorganic compounds disappeared, and the term lost their organic significance. But organic chemistry continued to be treated as a separate branch of chemistry, although it was given a new definition. Organic chemistry is now defined as the chemistry of compounds which contain carbon as an essential constituent. A few compounds of carbon, such as carbon monoxide, carbon dioxide, and carbonates, organic by above definition, are, however, studied in inorganic chemistry, which deals with the study of all other elements and their compounds. The simplest organic compound was hydrocarbon, which are made up of carbon and hydrogen. All other organic compounds can be considered to have been determined from hydrocarbon by the replacement of one or more hydrogen atoms by other atoms or groups. Therefore, organic chemistry can also be defined as the chemistry of hydrocarbon and their derivatives. Theoretical aspect of organic chemistry. There has been a strong growth of theoretical understanding in the field of organic chemistry in the last few decades. This have been very helpful in interpreting the details such as mechanism, rate of occurrence, and the effect of temperature, concentration, etc. of the large variety of chemical reactions encountered in organic chemistry. In order to appreciate the theoretical aspects of the subject, the students must have a clear understanding of certain fundamental concepts. We are introducing a few relatively simple concepts in this chapter. Now let us start 1.2. Nature of bonding in organic compounds. The carbon atom, atomic number 6, which is the common feature of all organic compounds, has the electronic configuration 1s2, 2s2, 2px1, 2py1, 2pz0. Thus, it has got 4 electrons in the valence shell. In order to acquire a stable noble gas configuration in its compound, carbon should either lose or gain 4 electrons or alternatively share 4 electrons. But the loss or gain of 4 electrons leading to the formation of C plus 4 or C minus 4 ion would require the supply of a very large amount of energy which is not available during ordinary chemical processes. This implies that carbon cannot form ionic bond in its compound and must form only covalent bonds. In other words, covalent bond is the bond of main importance in organic chemistry. According to orbital concept, a covalent bond is formed when a half-filled valence orbital of an atom overlap a half-filled valence orbital having an oppositely spined electron of another atom. Now a carbon atom has got only two half-filled valence orbitals, that is 2px1 and 2py1, and therefore it may be expected to form only two covalent bonds. But in actual practice, carbon is known to have a covalency of 4 in its compounds. To explain the tetracovalency of carbon, it has been postulated that at the time of bond formation, the 2 electrons in the 2s orbital of carbon are unpaired and one of them is promoted to the empty 2p orbital. This gives rise to electronic configuration 1s2, 2s1, 2px1, 2py1, 2pz1 as shown. Clearly shown that first of all the 2p has 2 electrons. After the promotion of electrons from 2s orbitals, there will be 1 electron left in 2s orbital and 1 electron will be promoted to 2p. And the 1s ground state of carbon atom and the excited state of carbon atom in 1s will remain same. In its new state called excited state, the carbon atom has 4 half-filled valence orbitals which would be available for the formation of covalent bond. Thus, carbon atom exists a covalency of 4. It may be noted that the formation of 4 bonds by carbon would result in greater lowering of energy and formation of more stable molecules that if carbon were to form only 2 bonds, this extra lowering of energy more than compensates the energy need to promote an electron from 2s to 2p orbital. This means that even though the promotion of electrons is by itself not favored energetically, since it takes place with the absorption of energy, it ultimately leads to greater lowering of energy by enabling carbon to form 4 bonds in place of only 2 as illustrated ahead. Here it is shown in the figure. Here it is shown that carbon in its ground state 2 half-filled orbitals plus 2H radical release of 2 into 418 kilojoule per mole of carbon CH bond will give HCH. C. Carbon ground state 2 half-filled orbital after absorption of 400 kilojoule per mole of carbon will give carbon with 4 lone pair electron, excited state 4 half-filled orbitals plus 4 H radical release of 4 into 418 kilojoule per mole of CH bond will give methane. Thus, there is a net release of 836 kilojoule per mole in the formation of CH2, while there is a net release of 1672 minus 400 will give 1272 kilojoule per mole in the formation of CH4, that is methane. Next topic is bond energy. The process of bond formation is accompanied by release of energy, and the bonded state represents a state of lower energy that the than the individual atom. It therefore follows that an equivalent amount of energy will have to be supplied to break the bond. The amount of energy required to break a bond and separate the bonded atom in the gaseous state is known as bond dissociation energy, or simply bond energy. It is generally expressed in kilojoule per mole. Thus, hydrogen molecule has a bond dissociation energy of 433 kilojoule per mole. H2 gas plus 433 kilojoule, that is bond dissociation energy, will give 2 H free radicals in gaseous state, each of 1 mole. It may be mentioned that bond energy is also equal to the amount of energy released when 1 mole of hydrogen atom combined with 1 mole of hydrogen atom to form 1 mole of hydrogen molecule containing 1 mole of hydrogen-hydrogen bonds, as H plus H, each of 1 mole will give HH, that is H2 1 mole plus 433 kilojoule. It is apparent that bond energy is a measure of the strength of a bond. Greater is the bond energy, stronger is the bond. Factors on which bond energy depend. First, size of bonded atom. Bond energy is inversely proportional to the size of bonded atom. The greater is the size of bonded atom, smaller is the bond energy. This is because in bigger size the overlapping of atomic orbitals is less effective. Bond length. The smaller is the bond length, higher is the bond energy. Smaller bond length means greater and stronger overlap of atomic orbitals, which result in greater bond energy. Nature of rest of the molecule. The energy required to break a particular bond between two atoms has a specific value only for that bond, and it is generally termed as bond dissociation energy. But when a certain bond may be present in molecule of different substance, the actual value of bond dissociation energy of that bond will vary from one compound to the another. For instance, OH bond may be present in water HOH as well as in methyl alcohol CH3OH. The bond dissociation energy of OH bond in water is different from its energy in methyl alcohol. In a polyatomic molecule, even the energy required to break a particular kind of bond may have different values. For example, the 4 CH bonds in methane, that is CH4, are equivalent, but the energy required to break the first bond, that is CH4, will give CH3 plus H, each of one radical, is not the same as the energy required to break the second bond, that is CH3 with one radical will give CH2 plus H radical, and so on. This difference in bond energy of even the same kind of bonds is due to the fact that the energy of a bond depend upon the nature of the rest of the molecules as well. Therefore, when giving the general values of the bond dissociation energy of such bonds, only the average value are stated. The average value are generally referred to as bond energies rather than the bond dissociation energy. The bond energy of some bonds are given in table 1.1. The value of bond energy given in the above table of HH, HCl, HBr and HI are their actual bond dissociation energy, while the values given for other bonds are the average bond energy. Localized and delocalized chemical bond. Localized chemical bond. When a chemical bond is formed by the overlapping of two atomic orbitals, the orbitals that results are the properties of the molecules, not of the individual atom. That is why the resulting orbitals are known as molecular orbitals. The electrons in these orbitals are shared between the atoms involved in bond formation. For example, let us consider the formation of a hydrogen bond from two hydrogen bonds, each having only one s electrons with anti-parallel spin. relative to the other. When the 1s orbital of the two atoms overlap, the two 1s electrons become paired and begin to overlap the same atomic orbital. The probability of finding other electrons is greater in the region between two nuclei. It is due to this concentration of negatively charged electrons between the two positively charged nuclei that the two nuclei are bonded together. It may be pointed out that even though between the electrons are negatively charged, they tend to concentrate in the internuclear region due to their anti-parallel spins. The net result is that electron density for the electrons involved in bond formation is greater in the region between the two nuclei. Therefore, the two electrons paired are said to occur a localized molecular orbital, and the bond form is known as localized bond. A localized bond may therefore be defined as the bond whose electrons are greatly concentrated in the region between the two nuclei only. A sigma bond between two atoms, a pi bond between two atoms in the molecule have only one double bond, or the pi bond in the molecules having isolated double bond are all localized bonds. Here in H2, the bond is localized sigma bond. In CH2, that is ethene, the localized sigma and pi bond is given in between them. In CH2 double bond CH, single bond CH2, single bond CH, double bond CH2, where the double bonds are there are localized sigma and pi bonds. All bonds shown above involved CH bonds are localized bonds. Delocalized chemical bonds. To understand the concept of delocalized chemical bonds, let us consider the case of a molecule containing double bond and single bond in the alternative position. Double bonds which alternate with single bond are said to be conjugated. For instance, 1,3-butanide is a conjugated diene, while 1,3-pentadiene is a non-conjugated diene having isolated double bonds. Here the structure of 1,3-butadiene and 1,3-pentadiene is shown, where 1,3-butadiene is conjugated alternating double and single bond, and 1,3-pentadiene is non-conjugated non-alternating or isolated double and single bond. Let us now discuss the molecule of 1,3-butadiene as a typical case of the formation of delocalized chemical bonds. Each of the four carbon atoms of 1,3-butadiene is in a sp2 hybridized state, having 3 sp2 hybridized orbital and 1 unhybridized p orbital. The 3 sp2 orbitals of each carbons are used in the formation of sigma bond with adjacent carbon and hydrogen atoms, and all these bonds are localized bonds. The unhybridized p orbitals of the carbon atoms are used in the formation of pi bond. Figure 1.3a shows unhybridized p orbital of the fourth carbon atom of 1,3-butadiene before the formation of pi bond. Overlap of p orbitals of 1c with that of 2c and of the p orbital of 3c and 4c is shown in figure 1.3b. However, if the molecule is planar, then the p orbital of 2c can also overlap the p orbital of 3c, just it can overlap the p orbital of 1c as depicted in figure 1.3c. This means that there is overlapping of p orbitals of 1c with 2c, 2c with 3c and 3c with 4c as shown in figure 1.3d. Therefore, all the 4 p orbitals can be treated as forming pi molecular bonds which covers all the 4 carbon atoms. Figure 1.3e. In this condition, we do not have pairs of electrons mainly confined to the region between two nuclei. In other words, the bond form are no longer localized. Therefore, a molecular orbital which is spanned over the nuclei of more than two atoms is known as delocalized molecular orbital, and the electron present in it are termed as delocalized electrons. The bond thus formed are called delocalized bond. A delocalized bond may be defined as the bond whose electrons are spread over the nuclei of more than two atoms, as in case of normal or localized pi molecular orbital. Delocalized molecular orbitals also consist of two electron clouds, one lying above the plane of atoms and the other lying below it. All these are shown in this. Electrons of delocalization of bonds. The delocalization of bonds has the following effects on the system involved. First, effect on the bond length. The formation of delocalized bond causes the bond length to change from the normal value of single, double and triple bonds. For example, the bond length between any two adjacent carbon atoms in 1,3-butadiene 149 picometer neither correspond to carbon-carbon single bond length 154 picometer nor carbon-carbon double bond length 134 picometer. Second, effect on movement of electrons. In delocalized bond, the electrons have greater freedom on movement than in localized bond. Third, effect on stability. The delocalization of bond lead to the decrease in energy of the system. In other words, delocalization of bond make the molecules more stable. This energy of stabilization is known as delocalization energy. For example, delocalization energy of 1,3-butadiene is nearly 16 kJ per mole. Kinds of molecules which contain localized bond. Delocalization of bonds is exhibited by three main kinds of structures. First, double or triple bonds in conjugation. Apart from 1,3-butadiene discussed above, benzene is another important example of molecules containing multiple bonds in conjugation which exhibit delocalization as discussed below. All the carbon atoms of benzene ring are in a state of sp2 hybridization. The three hybridized orbitals of each carbon are involved in the formation of three sigma bonds, two with the adjacent carbon atom and one with the hydrogen. As far as the unhybridized p orbitals of each carbon atom is concerned, it can overlap to a small but equal extent the unhybridized p orbitals of both the adjacent carbon atom. Here in this figure, sp2 hybridized carbons each forming 3 sigma bond is shown. That is, here the structure of benzene is shown. In the next figure, the possibility of overlap of p orbital in both directions is shown. Thus, the odd electrons in the unhybridized orbitals of each of 6 carbon atoms can form pi electron cloud involving more than 2 atoms. In other words, the pi electrons are spread over or extensively delocalized, and this results in the formation of a molecular orbital embracing all the 6 carbon atoms. The net result of this localization is that there are two continuous rings like electron clouds, one lying above and the other lying below the plane as shown in this figure. The delocalized bond in carbon atom between the carbon atoms in benzene is shown in this figure 1.4. Second, double or triple bonds in conjugation with a p orbitals on an adjacent atom. The presence of a p orbitals which may have 2, 1 or no electron on an atom adjacent to a multiple bond also lead to the formation of delocalized bond. For example, in vinyl chloride CH2 double bond CH single bond Cl, The p orbital of chlorine atom having a lone pair of electron overlap with the carbon-carbon double bond to cause delocalization as shown in the figure on the right hand side. Allylic carbanion CH2 double bond CH single bond CH2 with a negative charge in lone pair afford another example of a structure exhibiting delocalization in which the p orbital on adjacent atom contain one electrons are found in free radicals, while the structures in which the p orbital does not contain any electrons are come across in carbocations. Third, hyperconjugation. The type of delocalization involves CH sigma bond adjacent to multiple bonds and is discussed later in session 1.8. 1.5 Van der Waals interactions. Intermolecular forces. Intermolecular forces are the attractive forces which operate between molecules of the same or different substances. These forces can be divided into different types depending upon the nature of the molecules. For instance, in covalent compounds containing polar bonds, partial negative and partial positive charges are produced on atoms by unequal sharing of electron pair. As a result, majority of these molecules possesses a dipole moment. In some cases, the negative end of one molecule will naturally attract the positive end of another molecule to give rise to intermolecular forces known as dipole-dipole interaction. However, non-polar molecules also have weak intermolecular forces as discussed below. Non-polar molecular substances such as oxygen, nitrogen, chlorine, and methane exist in the gaseous state in the form of individual covalently bonded molecules. But even such substances, as well as the noble gases, undergo condensation at low temperature to liquid and solid state, which is accompanied by decrease of energy. This led to the suggestion by Van der Waals, a Dutch physicist, that there must be some weak intermolecular interaction between such molecules which become relatively stronger in the liquid or solid state. Subsequently, these forces come to be termed as Van der Waals forces or interactions. They may be defined as very weak force of attraction between non-polar molecules which arises from the movement of electrons in atoms and molecules. That these forces are quite weak is evident from the fact that non-polar molecules, substances, and noble gases have very low boiling point. This can be possible only if the intermolecular forces are weak and are overcome by supplying very small amount of energy. 1.5.1 Origin of Van der Waals forces. To understand the origin of these forces, let us consider two helium atoms very close together. Ordinarily, in each carbon, the charge of an electron is symmetrically distributed across its nucleus. However, since the electrons move above freely, we can imagine that at a particular instant of time, millionth of a second, the electron distribution in atom 1 becomes somewhat unsymmetrical with a slight increase in electron density on one side. Therefore, for a very small fraction of a second, these atoms have one end very slightly negative relative to the other, and this temporary separation of positive and negative charge possesses an instantaneous or temporary dipole. Here in figure 1.5, the origin of temporary dipole is shown. First of all, originally the negative charge of an electron is distributed symmetrically. Then in this figure, for a very short period, the electronic charge is spent more on one side of an atom than on the other side. This produces a temporary dipole. In figure 1.6, dipole on one atom can induce a dipole on a neighboring atom. Such as in first, it is shown that the dipole already present, and second figure, this dipole is induced by the first dipole. The temporary dipole in turn influence the electron distribution of another atoms present in its neighborhood, because the negative end of atom 1 repel the electrons of atom 2. As a result, there is an instantaneous induced dipole in the neighboring atom, although this picture persists for an extremely short time, and the momentarily and induced dipoles are consequently changing. The net result is a force of attraction between the neighboring atoms. Similarly, in case of non-polar molecules such as methane and carbon tetrachloride, the average distribution of charge above the molecule is symmetrical and there is no net dipole moment. However, the instantaneous increase or decrease in electron density in a particular region creates very short lived temporary dipole in portion of the molecule. These dipole induce oppositively oriented dipoles in neighboring molecules, so as to result in a net attraction between different molecules. The force of attraction between non-polar molecules due to temporary dipole-induced dipole interaction constitute van der Waals interaction. These are also known as or dispersion forces. 1.5.2 Factor influencing van der Waals forces. As already remarked, the van der Waals forces are very weak and effective over extremely small distance. The actual manufacture of these forces depend mainly upon the following facts. First, number of electrons in the molecule. The magnitude of van der Waals forces depend upon the number of electrons in an atom or a molecule. With the increase in the number of electrons, there are more chances of the electron distribution to become unsymmetrical. As a result, the magnitude of van der Waals forces increase. Second, size of the molecule. As the molecular size increases, the surface area becomes larger. Consequently, the chances of unsymmetrical electron distribution increases and the van der Waals forces also become stronger. Since the increase in the molecular size generally runs parallel to the increase in the molecular weight for same type of substances, therefore the van der Waals forces also become negatively stronger with the increase in molecular weight. This is why the boiling point of a series of similar compounds generally increases as the molecular weight increases. For instance, the boiling point of alkanes increases gradually from methane to ethane to propane and so on. Third, molecular shape. The magnitude of van der Waals forces also depend upon the shape of molecule. To elucidate this statement, let us consider the case of N-pentane and neopentane. N-pentane is a straight chain molecule having a large surface area, while neopentane is a compact molecule having much lesser surface area. Here the structure of N-pentane, larger surface area, greater magnitude of van der Waals forces is shown, and neopentane, which has less surface area, lesser magnitude of van der Waals forces. Due to greater surface area of N-pentane, there are much more chances of the molecules of this compound to interact with each other. As a result, the magnitude of van der Waals forces is large. On the other hand, the chances of molecular interactions are much less in neopentane due to the compact shape of the molecules, and the magnitude of van der Waals forces is very small. That is why neopentane has a much lesser boiling point, 283 Kelvin, than N-pentane, 309 Kelvin. Fourth, temperature and pressure. It may be noted that for the same substance, the van der Waals forces are relatively stronger at low temperature and high pressure. At low temperature, the random movement of the molecule decreases, while provides greater opportunity for molecule interaction. Naturally, therefore, the van der Waals forces are relatively stronger. At a high pressure, the molecules get closer, so that there is a stronger interaction between neighboring molecules, and therefore the van der Waals forces are also stronger. Types of van der Waals interaction. It may be noted out that apart from intermolecular forces between non-polar molecules due to temporary dipole-induced dipole interaction, the term van der Waals interaction also includes the following two types of attractive forces. First, dipole-dipole attraction. As already stated, these are forces of attraction which operates between molecules which are permanently polar in nature, such as HCl, NH3, SO2, and acetone. Second, dipole induced dipole interaction. These forces operate between molecules of one of which is polar and the other is non-polar. Under the influence of polar molecules, a temporary dipole is induced in the non-polar molecules. This gives rise to dipole induced dipole kind of interaction. For example, there is a weak interaction of this type between water molecule and xenon gas, due to which xenon gas is sparingly soluble in water. Van der Waals repulsion. The magnitude of van der Waals forces of attraction increases as the distance between the non-bonded atoms on the molecule decreases. The attraction become maximum when the distance between the non-bonded atoms or molecules reaches a certain minimum value. This minimum distance at which the force of attraction is maximum is equal to the sum of van der Waals radii of the non-bonded atom or molecule. If non-bonded atom come so close to each other that the distance between them is lesser than the sum of their van der Waals radii, the attractive interaction turns into repulsive interaction. For example, in both configuration of cyclohexane, there is repulsive interaction between flagpole hydrogen. This is because the distance between them is 183 picometer, which is less than the sum of their van der Waals radii, 250 picometer. Please refer to the board configuration of cyclohexane, section 3.25. 1.6 Resonance. It has already been studied in earlier classes that the concept of resonance or mesomerism was put forward to explain the structure of compounds such as benzene. It has been suggested that if a molecule can be assigned two or more conventional valence bond structures, each of which can explain most but not all the observed properties of the compound, the actual structure lies somewhat in between the various possible conventional structures. The various possible structures are called contributing or canonical structures, and the actual structure is known as resonance. Hybrid is indicated by putting a double-headed arrow between the contributing structures. The concept of hybridization of two or more conventional valence bond structures to arrive at an entirely new and individual structure, which however cannot be depicted on paper in terms of a conventional formula, is termed as resonance. One of the most well-known examples of the application of resonance is afforded by benzene. Since benzene could not be assigned any satisfactory valence bond structure which could explain all these properties, it was proposed that benzene is a resonance hybrid of structure 1 and 2. This implies that the structure of benzene is represented neither by 1 nor 2 but lies but lies somewhere in between the two. It is evident that in the resonance hybrid, the bond which link the carbon atom neither correspond to single nor double bonds. On the other hand, all the bonds are equivalent and are intermediate between single and double bond. This has been confirmed by X-ray diffraction studies, which shows that all the carbon-carbon bond in benzene are of exactly the same bond length, which is in between that of carbon-carbon single bond and carbon-carbon double bond length. The resonance hybrid structure of benzene has 151 kJ per mole of energy, lesser than either of the contributing structures. This represents the resonance energy of the molecules. It is this energy which is responsible for the unusual stability and remarkable behavior of the molecule. Note, the concept of resonance does not mean that any one molecule of benzene spent a part of its time in structure 1 and the rest of the time in structure 2. It also does not mean that some molecule of benzene have got structure 1 and other have got structure 2. What resonance means is that any one molecule of benzene always has the same single structure which is identical with that of any other molecule and is intermediate between structure 1 and 2. Other example of resonance: 1. Carbon dioxide. Carbon dioxide is considered to be a resonance hybrid of 3 contributing structures as shown below. The observed bond length of carbon oxygen bond in carbon dioxide 115 picometer is lesser than that of carbon oxygen double bond 122 picometer, which can be justified in terms of its resonance hybrid structure. Second, carboxylic acid. The acidic character of carboxylic acid is explained by treating the carboxylic acid as a resonance hybrid of the following contributing structures. Here the resonating structures of carboxylic hybrid are shown. Third, 1,3-butadiene. 1,3-butadiene and other conjugated diene also exhibit a resonance hybrid. For example, 1,3-butadiene is a resonance hybrid of 3 contributing structures. Use of curved arrow to show the interconversion of contributing structures. Since contributing structures differ from each other only in the position of electron, curved arrows are often used to show the flow of electrons in the conversion of one structure into another. This makes it easy to draw the various contributing structures of a given species. For example, the contributing structures of carboxylic acid may be drawn as follows. Similarly, the contributing structure of 1,3-butadiene may be drawn as follows. Condition for resonance. According to the general theory of resonance, the various contributing structure formula constituting to the structure of resonance hybrid must satisfy the following condition. First, the various contributing structure shows differ from each other only in the position of electron, pi electron and lone pair of electrons, whereas the relative arrangement of atoms or atomic nuclei to be more precise and their state of hybridization must be the same. Note, it may be recalled that existence of a structure having the same molecular formula but different relative arrangement of atomic nuclei lead to the phenomena of isomerism. Second, the atoms involved must lie in the same or nearly the same plane. The number of paired or unpaired electrons in each contributing structure must be the same. For example, CH2 CH double bond CH CH2 It is not valid contributing structures for butadiene CH2 double bond CH double bond CH2 since it has more unpaired electrons than other contributing structure. All the contributing structure must show the correct number of valence electrons for the elements of second period. No contributing structure should have more than 8 electrons in the valence shell of the electron element. For example, CH2 CH double bond NH3 cannot be considered as contributing structure since in it nitrogen has 10 electrons in the valence shell, which is not possible. Fifth, all the contributing structures should have the same or nearly the same amount of energy and stability. When the contributing structures differ in energy content or relative stability, the more stable structure makes greater contribution towards the resonance hybrid. In determining the relative stability of contributing structure, the following point may be noted. First, larger the covalent bond in a structure, greater is the stability. For example, CH2 CH double bond CH2 CH double bond CH. Second, the structures involving separation of positive and negative charge are less stable than that which do not involve any separation of charge. When atoms of different electronegativity are involved, the structures having negative charge on more electronegative atom and positive charge on less electronegative atoms are relatively more stable than the other way round. For example, in the figure shown. Fourth, the structures having like charges on adjacent atoms are highly unstable. Eighth, the more the number of contributing structure, the more stable is the resonance hybrid. Properties of resonance hybrid. A resonance hybrid is always more stable than any of the contributing structures. The extent of greater stability of the resonance hybrid depend upon the number of contributing structures and their relative stability. Second, resonance energy. It is a measure of stabilization due to resonance and may be defined as the difference in energy between the energy of a resonance hybrid and its more stable contributing structure. Greater the resonance energy, greater is the stability of resonance hybrid. For example, the resonance energy of benzene is about 151 kilojoule per mole. The value of resonance energy can be determined from the data involving heat of hydrogenation and heat of combustion, etc. Third, bond length. In a resonance hybrid, the bond length are different from those in the contributing structure. For instance, the carbon-oxygen bond length in carbon dioxide is 1.15 angstrom or 115 picometer, or against the value of 1.22 angstrom or 122 picometer for a carbon-oxygen double bond length. It may be seen that the concept of resonance hybridization is essentially equivalent to the delocalization of electrons. It is this delocalization of electrons which lead to the formation of stronger bond and much stable molecule. Therefore, the term delocalization energy is often used in place of resonance effect. It is a process of permanent displacement of electrons in a molecule brought about by resonance or mesomerism, generally designed or R or M effect. Unlike inductive effects, resonance or mesomeric effect is transmitted through pi electrons or operate in unsaturated system, particularly those containing a stable molecule or group in conjugation with the unstable substance. For this reason, it is also termed as a conjugative effect. What happens is that the resonance effect causes delocalization of electrons and give rise to addition contributing structures due to the withdrawal or release of electrons by the given groups. For example, in molecule CH2 double bond CH double bond O, which contains C double bond O group in conjugation with C double bond C, electron withdrawal by C double bond O group causes delocalization of electron and give rise to addition structure as shown below. Hyperconjugation or no bond resonance. The concept of hyperconjugation was put forward by Baker and Nathan 1935 as a result of a certain observation concerning the inductive effect of alkyl groups attached to a unsaturated system such as a double bond on benzene ring. An alkyl group has electron releasing inductive effect plus I effect, and the order of plus I effect of different alkyl groups is, first of all, the tertiary will come, then the secondary, then the primary, and then methyl group will come. But when an alkyl group is attached to an unsaturated system such as a double bond or a benzene ring, the above order of inductive effect gives reversed. To account for these observations, Baker and Nathan put forward the concept of hyperconjugation, as also referred to as Baker-Nathan effect. Hyperconjugation is another kind of resonance or delocalization of electrons which takes place through overlapping between a pi orbital or a p orbital and a sigma orbital of an adjacent CH bond. For instance, let us consider the delocalization of electrons in alkenes CH double bond CH2, where CH represents an alkyl group attached to C double bond C. The delocalization here may be shown as below. It is clear that the delocalization involves overlapping between a sigma bond of CH bond of alkyl group and pi orbital of C double bond C bond. As a result of this overlapping, each of the delocalized electrons is involved in binding together not merely two atoms, but it is helps in binding together all the four atoms to some extent. In terms of resonance, the above situation may be taken to mean that the given alkene is a resonance hybrid of canonical forms such as structure 1 and 2. It may be seen that the resonance is not forming any real bond in structure 2. Therefore, hyperconjugation is sometimes called no bond resonance. It is important to remember, however, that in actual practice, hydrogen is not free to leave its original position because structure 2 is highly unstable and makes only minor contribution to resonance hybrid, which resembles structure 1 very closely. Application of hyperconjugation. The concept of hyperconjugation is widely used in the study of organic chemistry. For example, it helps to explain the relative stability of alkenes. Second, it is used to explain the relative stability of carbocation and free radicals. 1.9 Inductive effect. The concept of inductive effect concerns the shift of electrical charge within a molecule arising out of the presence of a polar covalent bond in the molecule. To illustrate this, let us consider a molecule having a chain of carbon atom with a chlorine atom linked to the end of carbon atom, such as 4C, 3C, 2C, 1C, Cl. Due to greater electronegativity of chlorine, the electron pair of the bond between 1C and Cl is displayed towards a chlorine atom. As a result, polarization of the bond takes place. Chlorine acquires a small negative charge while one carbon becomes slightly positively charged as shown in the figure. Now the positively charged ones 3 exist an attractive influence upon the electron pair shared between 1c and 2c due to the res- resultant electron displacement towards 1c. The positive charge on 1c is particularly neutralized while a small positive charge develops on 2c, but the charge on 2c is smaller than that of 1c. The positively charged 2c in turn attract the electron pair of the bond between itself and 3c, thereby making 3c also very slightly positively charged. This process of electron shift along the chain of atoms due to the presence of a polar covalent bond in a molecule is known as inductive effect. It is represented by an arrow as shown in this figure. Inductive effect is sometimes also called transmission effect because it is transmitted through the bond consisting the chain of atoms. It should be noted that the effect along the chain of atoms is not the same throughout. It decreases sharply as we move along the initial polar bond and is negligible from fourth atom upwards. It must also be understood that inductive effect does not involve any actual transfer of electrons from one atom to the other. It merely helps in displaying them permanently. Types of inductive effect. Inductive effect is a relative effect and may involve attraction of electron towards a group or repulsion of electrons away from it. For comparing the relative inductive effect of various groups, hydrogen is commonly taken as the standard, and accordingly groups are divided into two categories. First, electron withdrawing or attracting inductive effect, denoted as -I effect. Atoms which have greater electron attracting capacity than hydrogen are said to have -I effect. The decreasing order of -I of some common groups are as shown in figure. It may be noted that compared to hydrogen, most groups are electron withdrawing. Second, electron releasing or repelling inductive effect, denoted as +I effect. Atoms or groups which have lesser electron attracting capacity than hydrogen are said to have +I effect. The most important electron releasing groups are alkyl groups. At the same time, many groups having formal negative charges and atoms of lower electronegativity such as Si, Mg and Li are electron releasing. The decreasing order of some groups having +I effect are as shown in this figure. It may be noted that in case of alkyl groups, the more highly substituted the alkyl group, the greater is its +I effect. Comparison of resonance and inductive effect. Resonance effect. Resonance effect operates in unsaturated system, particularly in a conjugated system through the pi electrons. Inductive effect. It operates even in saturated system. Presence of unsaturation is not a necessary condition. Resonance effect. It involves displacement of non-bonding and pi electrons. Inductive. It involves displacement of sigma electrons. Resonance effect. During the resonance, electron pairs is completely transferred, leading to the development of fully positive and negative charge. In inductive effect, the electron pair is only slightly displaced from its position so that only partial positive and negative charge appears. Resonance effects lead to the delocalization of electron, while inductive effect there is no delocalization of electron takes place. It is transmitted over large distance without undergoing any change in intensity, it decreases sharply with the increase in distance and operates only over short distances. Electromagnetic effect. Electromagnetic effect is a temporary phenomena which operates during some reacting involving molecules containing double or triple bond. It consists of an interstaneous or complete transfer of a shared pair of electrons of the multi-bond to one of the bonded atoms due to the requirement of some attracting reagents. Electromagnetic effect is usually denoted as E effect, and the transfer of electron taking place is represented by a curved arrow as shown in this figure. Since A loses its share in the electron pair to B, A acquires a positive charge and B gives a negative charge. This structure is evidently not as stable as the normal structure and is formed only at the moment of reaction under the requirement of attracting reagents. If the attracting reagent is withdrawn without the reaction being allowed to take place, electron distribution reverts to its normal stage. In other words, electromagnetic effect involves temporary polarization at the seat of multiple bond. An inductive shift of electromagnetic shift of electrons precedes more reactions involving addition of multiple bonds. Let us for instance consider a molecule containing carbonyl group. When a reagent such as Cn negative ion attracts the carbonyl group, one of the shared pair of electrons, the pair constituting the pi bond, is transferred to oxygen. As a result, the carbon atoms become positively charged while oxygen acquires negative charge, and the attractive reagents immediately forms a bond with the positively charged carbon as depicted below. It is quite obvious that the electron pair cannot be transferred to the carbon atom because oxygen is more electronegative as compared with carbon. Types of electromagnetic effect. Electromagnetic effect can also be divided into two types of explained below. First, plus I effect. Plus E effect. When the pi electron is transferred to that atom of a multiple bond which got bonded to the attracting reagent, electromagnetic effect is known as plus I effect. For example, ethene plus H positive. This H positive will go on, first of all, the one bond from the double bond will go to one carbon atom. It will acquire negative charge, then H positive will attracted to that atom and the other carbon atom will acquire positive charge. Minus I effect. When the pi electron are transferred away from the bond of multiple bond which get bonded to the attractive reagent, electromagnetic effect is known as minus I effect. We have taken CO, carbonyl group, plus Cn negative. CO, first of all, the double bond, one bond will move to oxygen, it will acquire partial negative charge and carbon will acquire partial positive charge, so Cn will move to carbon positive charge. Next is the significance of electromagnetic effect. Electromagnetic effect is very helpful in explaining the mechanism of addition reaction of organic compounds containing the multiple bonds, as well be shown at different places in the text. If both inductive and electromagnetic effect operate together, these may assist or oppose each other. In case they are opposed to each other, the electromagnetic effect are generally overcome the inductive effect. Comparison of inductive and electromagnetic effect. Inductive effect. It is a permanent effect which involves a mere displacement of electron. Electromagnetic effect is a temporary effect which involves the cleavage of a multiple bond and the complete transfer of a shared pair of electrons to one of the bond. Inductive effect, there is only a distortion in the shape of molecular orbitals containing the placed electrons, the electrons do not leave the molecular orbital. Electromagnetic effect. The electron pair of the multiple bonds leaves its molecular orbital completely and is transferred to one of the atom. Inductive effect. Third, the only requirement for this effect to operate is the presence of some polar bond in the molecule. It is not necessary for the molecule to contain a multiple bond. Electromagnetic effect can be exhibited only by molecules containing at least one multiple bond, which may or may not be polar in nature. Inductive effect do not require any outside attracting reagent. Electromagnetic effect can take place only under the influence of an attractive reagent. Inductive effect involves a partial separation of charge, whereas electromagnetic effect involves a complete separation of charge. So our chapter is completed. Thank you.